So I have started the recording now. So I welcome you all to the second week of the live sessions for the course Basics of Finite Element Analysis Part 2. The course instructor is Professor Dr. Nachiketa Tiwari from IIT Kanpur. So introducing myself, I am Vikram Balaji, a research scholar from the Department of Mechanical Engineering at IIT Madras. So we will see the week 2 contents. So as you might have seen in the lecture, there are 4 topics. So can anybody once again verify whether I am audible?
Sir, you're audible.
Okay. So we'll now go into the contents. Are you able to see the screen?
Yes, sir.
Okay. So these are the week 2 contents which you might have seen in the lecture. So the topics are first one, the sources of error in FEA solution. Second is the measures of errors in FEA solution. There are different measures which you would have seen. Third is the convergence of solution. What are the procedure for a solution to converge? And lastly, we might have seen how accurate a solution is. So we will now go into the sample assignment questions. We will see some questions one by one, through which we will be able to understand some concepts of related to the week 2 contents. So this is the first question. So which of the following will decrease the error? So there are 4 options given. So first one is increasing the number of elements. Second is increasing the order of shape functions. Third is increasing the number of decimals in numerical values. Fourth is all of the above. So any guesses as to which is the correct answer?
Sir, D, all of the above.
Okay. So D, all of the above. So yes, your correct answer is option D. So basically all the given options will able to help us decrease the error. So we'll go to the next question. So the type of error associated with choice of the shape function representing the primary variable. So which of the following is the answer for this question? The first one is approximation error. Second is computational error. Third one is computational domain error. Fourth is none of the above. So can you take a guess? So type of error associated with the choice of shape function.
Sir, approximation error A.
Okay, approximation error. Okay, so we'll see the answer. Yes, you are right. Approximation error. So basically, there are 3 types of error which you might have seen. So approximation error deals with the error which is associated with the assumption of the polynomial for the shape function representing the primary variable. So we'll now go to the next question. So which of the following type of error is not likely to occur during a one-dimensional FE analysis? So one-dimensional FE analysis means your domain is basically of a single dimension. Let's say x. So this will be your domain. Maybe starting from x is equal to 0 to some value. Let's say x is equal to L. So this is your one-dimensional FE analysis. So which of the following type of error is not likely to occur during the one-dimensional FE analysis? So again, the same options are given. Approximation error, computational domain error, none of the above. So can you take a guess as to which would be the answer? Not likely to occur. Can just take any just can take a guess if you are not sure also. That's not a problem.
Sir, C, computational domain error.
Okay, computational domain error. Okay, so let us see the answer. Yes, you are right. So why this is the answer is, suppose this is our one dimensional. So while we are discretizing the domain, we are going to divide this domain into multiple elements. So you can see that while discretization, there is no portion of the domain which is left behind. So this need not be the case for a two dimension. Say you have a circle, you are going to discretize the domain. So maybe you are going to discretize into some eight elements. So each will be some two dimensional shape. So if I connect this, the domain, you can see that there is some portion of the domain which is left behind, which is not able to be discretized properly. So but that is not the case in the one dimensional case, where when you are discretizing the domain, you are dividing the domain into multiple elements. So each portion of the domain is covered in one element or the other. So option C is the answer. So I hope there is no doubt in this. So we'll go to the next question. So the question is, if double bar E, so EM denotes submetric error. So then the value of M. So this is a kind of a measure of error which is called a submetric error. So if this denotes submetric error, then what could be the value of M? So there are four options. Option A is 0, option B is 1, option C is infinity, option D none of the above. So can you again take a guess as to what could be the answer? So first of all, do you know what is submetric error?
No, sir.
Okay. So can you recall what are all the type of errors, the measure of errors that you came across in the week 2 lecture? So the names at least. What are all the names which you came across? Do you recall anything?
Sir, sources of error we have come across the discretization of element, numerical errors,
Yes,
computational errors.
correct. So those are all source of error. So you have approximation error, then you have the computational error. So under computational error, you have two types. One is with the arithmetic error, and another is the quadrature error. And third one is the domain error, which we saw just now, computational domain error. But other than this, there is something called as the different measures of error. So that also would have come across, right? So are you able to recall?
Yes, sir. Yes.
Yes. So can you recall what are the types we would have seen? Okay, so I'll just write the names so you can see whether you're able to. First is the pointwise error. Okay, so that is first one. Second is, you have something called as max norm. This you can write it as submetric. Third is energy norm, you can say. Fourth type of error is measure is L2 norm. So these names are you able to recall?
Yes, sir.
Yeah, so there is one thing called a submetric error, which is max norm, right? So each will have some symbol. So this E which I have indicated here, this is nothing but your U minus UH, correct? So U is your exact solution, UH is your solution due to FEA solution. So here you would have seen there will be some kind of a subscript. It could be M, whatever. So if this M for submetric error, can you say what is this M? What could it be? That is a question. Can you take any guess? Even if you are not sure about the answer, you can just guess. We'll see whether it is right or not. So shall we go to the answer?
Yes, sir, sure.
Okay, yeah. So actually answer is C. So point wise we do not have any such thing. It's just your u minus u of x minus u of h. So you don't have any notation like this. So max norm you can say that it is nothing but u minus uh at infinity. For energy norm the same would be u minus at m. So this is some m we can say. We'll see what this m is in the subsequent question. So L2 norm you can say that it is u minus at 0. So what this means is max norm is it's nothing but the maximum possible error. It could be any location. So for example if you have a function like this, so this is your domain is a one dimension. So from 0 to, so not 0, let us say from x1 to x2. So this is your u and this is your this thing. Just erase this part. Yeah. So this is your FE solution, let's say. So you can say the maximum error is somewhere you can say is at this point. So if you see the symbol, this subscript is nothing but infinity. So answer is C. So this is just nothing but a notation. There is no any significance to this notation for this. However, for the energy norm, you will see in the next question that there is a significance for this subscript. So and again L2 norm also there is a significance for the subscript 0. So for max norm, which is nothing but submetric, your subscript is infinity. So any doubt in this question? So it's just a notation. There's no any significant meaning attached to it.
No, sir.
Okay. So we'll proceed to the next question. Okay. Same thing. So actually I discussed the answer in the last question itself. So if EM denotes a L2 norm error, so the value of M. So just now we saw the value of M for different errors, right? So can you guess now? Whether it's 0, 1, infinity or none of the above for L2 norm.
Sir, 0, sir.
Yeah,
A.
0. Okay. Yes, you're right. So if we just went to the last question, we had seen for different norms what is the uh, subscript. Okay. So next question. So if energy norm of a FE solution to a differential equation can be expressed symbolically as modulus, this double modulus of E to the subscript base 2, then the order of the differential equation. So as I told you in the last question, last to last question, there is a significance attached to this subscript. So in the case of energy norm, so we saw that E of subscript m. Here I am mentioning that m is equal to 2. So this has some connection with the order of the differential equation. So can you guess what could be the answer for this question? Can you recall like what was the link between the subscript and the order of the differential equation from the lecture? Are you able to recall? Like, do you remember?
Sir, maybe C, sir, 4.
Okay, so one guess is 4, correct. So we'll see the answer. Yes, you are correct. Answer C is 4. So actually, if you would have observed in the lecture, so when your energy norm is symbolized as E to the base m, so order of the differential equation is nothing but 2m. So 2 times 2, 4. So yes, option is answer is option C. Okay. So next one. Okay. So which of the following measures of error is used for checking the convergence of a FE solution? So we just saw the different types of errors, right? Measures of error. So among this, which of the following is used for checking the convergence? So you might know that there is some criterion for convergence of a FE solution. So can you recall which of the following type of measure of error is used for checking the convergence? So four options: pointwise error, submetric error, L2 norm error, and energy norm. Any guesses?
Sir, point wise, maybe A.
Pointwise. Okay. Mm, okay. So actually, we'll see exactly what the convergence criterion is. I'll just now indicate here. So we have some U minus UH. This could be anything. So based on what is this subscript, so something it will be less than or equal to some expression. So this is the expression. This is the basic expression for your this thing. So the question here is, what is this? Is it pointwise error? Means is it does it not, it does not have anything to do with this double modulus. So if it was submetric, then it would have been infinity. If it was L2, then it would have been 0. If it was the energy norm, it would have been M. So we'll see the answer. Answer is actually, sorry, it should be D, energy norm. Answer is D. So why is it D? Let us see. So your expression is actually E to the base M is less than or equal to C into some H power P. So this is the equation. But here if you see the modular, the subscript used is M. It is not 0 or infinity or this thing. If pointwise errors, there will be it will not be any this thing. There will not be any double modulus at all. So actually answer should be energy norm error. So we check the energy norm error for the FEA solution, and that it has to satisfy this expression. So that is the uh, procedure for checking the convergence of the FEA solution. So any doubt in this question?
No, sir.
Okay, so it's actually the energy norm error. So we have to be aware. So whenever we are going to check the convergence of FEA solution, the measure of error which we are using for checking the convergence is nothing but the energy norm. So actually, can you say what is the expression of this energy norm? We have this thing, right? We have this M. So let us say M is equal to some equal to 1. So what is the energy norm? So actually, so is it related to just to UH, or is it related to some derivative terms?
Uh, Maybe not a derivative term, but the UH.
Okay. So actually, your thing is, I'll just erase this. So definition of energy norm is E subscript m is equal to, so your integral, so from domain, so let us say we have one dimensional domain, so let us say x equal to a to x equal to b. So from a to b integral, so summation I is equal to 0 to m. You have some differential terms, d of power I of u by d x power I minus d power I of uh by dx. So this thing modulus the whole square into dx, the whole thing I am going to take the square root. This is the definition of energy norm. So are you able to recall? This is energy. This is the expression for energy norm.
Yes, sir.
Correct, right? So if I put m is equal to 1, so for I is equal to 0, what would be this thing? It will be just u minus uh, because there is no differential at all. So for I is equal to 0, it will be simply u minus uh. So that is what is your L2 norm. So if m is equal to 0, sorry. Sorry, I equal 0 and m is equal to 0 also. So you will have only have u minus terms. You will have this whole square. You will have this dx integrated from a to b, and you have the square root. So this is for I is equal to 0. So if you have I is equal to 1, then you have du by dx. If I was equal to 2, then you have d square u by dx square. So energy norm, based on your m value, it will have some derivative terms also. So usually, as we saw earlier, if order of the differential equation is 2m, then suppose if you have a second order differential equation, then your m will be equal to 1. So if m is equal to 1, then you will have uh, a differential term also. So not necessary that it will be only a terms without differential terms. So here if you see, this is nothing but your L2 norm error. That is why we have this subscript of 0, because you have only the primary variable term and we do not have any differential terms. So if this was instead of 0 it was 1, then you have plus, then inside the integral you will have plus d du by dx minus duh by dx. So this also you will have. This also will have inside this square root. So this also you will have inside. So any doubts? So we basically use the energy norm error for checking the convergence, and this is the expression for the energy norm. So any doubts in this? Also. So shall we proceed to the next question?
Yes, sir.
Okay. Yes. So as I wrote in the last question, you have the convergence statement given here. So this is CH power P. So here the question is what does H indicate? So there are four options. First option is your element size. Second option is degree of polynomial of approximation function. C is the order of the differential equation, and D is the domain size. So can you guess what could be the answer? Any guesses? So what does H indicate?
Sir, A element size.
Okay, so we'll see the answer. Yes, you are right. H indicates the element size. So this is nothing but, as I said, so since you are using M, so this is nothing but your energy norm. This is your energy norm. So energy norm is less than or equal to some expression which is nothing but C times H power P. So in this, H indicates the element size. Element size. So any doubt for this?
No, sir.
Okay. So next question. So same thing. So again we are dealing with the convergence statement. The energy norm is less than or equal to Ch power P. So P can be increased by. So there are four options. There are one is increasing the element size. Second is increasing the degree of polynomial interpolation function. Third is increasing the order of the differential equation. Fourth is decreasing the element size. So this P is somehow dependent on one of these one or two of these options here. So but only one answer is correct. So how to increase the P? So we'll actually see what is P later. So there is an expression of P which depends on one or more of these options which are listed here. However, only one answer is correct. So can you guess what could be that correct answer? So first option is increasing the element size. Second option is increasing the degree of polynomial interpolation function. Third is increasing the order of differential equation. And fourth is decreasing the element size. Any guesses?
Sir, increasing the element size A.
A, okay. Increasing the element size. So this is one of the guess. So any other guesses? Okay. So okay, we'll see the answer now. Actually answer is B. Increasing the degree of polynomial interpolation function. Sorry. So why is it B? We'll see. So can anybody say what is P? P stands for in this expression? Energy norm is less than or equal to C into H power P. Any guesses as to what P indicates? It's actually the rate of convergence. So there is an expression for P actually. So P is equal to. So can anybody guess what is this expression for P? Are you able to recall? Okay. So I'll write the expression P is equal to K plus 1 minus M. So is this are you able to remember what this expression means? So can you guess what is K and what is M? Any? So K and M, anybody? Okay, so k is nothing but your order of, sorry, not order. So this is your degree of polynomial. So m is nothing but, so 2m is the order of differential equation. So we just saw this earlier. So increase, so p can be increased by either increasing k or decreasing m. Again, sorry. So if I increase k, which is nothing but increasing the degree of polynomial interpolation function, I can increase my p. At the same time, increasing the order, so m increases, p decreases. Sorry. So any doubt as to why b is the answer? So we just saw the expression for p. So increasing the degree of polynomial interpolation function will help us to increase the convergence, rate of convergence, that is p. So any doubts?
No, sir.
Okay. So we'll now go to the next question. So which of the following represents the correct nature of the graph? So we have the log of the energy norm in the y-axis and log of h at the x-axis. And there are four types of curves which are there. So one is a straight line, uh, which is having a slope like this, increasing slope, which is increasing nature. The second one is a straight line but of a decreasing nature. Third is a non-straight line, it's a curved path, and fourth is also curved. Third is like you can say it's a concave. Fourth is a convex kind of thing. So any idea what would be the answer for this? You can take any. You can just try to guess.
It will be a straight line, sir. One.
Yes, one. Okay. Oh, yes, you are right. Answer is one. So why is it one? So it's because of the expression. So we just saw. So em is less than or equal to c times of h power p. So we'll assume the rare case where this is equal. So let us say is equal to c h power p. If you take the logarithm of both sides, log of c h power p. So this can be split into log of c plus log of h power p. So this is nothing but log c plus p times log of h. So if you plot a equation with this as y and this as your x, so y is equal to, it is of the form, oh sorry, y is equal to mx plus c. So where your m is the slope. So it is a straight line. And your slope is equal to p. So this is why answer is 1. So it is a straight line with this thing, slope is p. And why is it not 2? Why is it 1? Can you guess?
Sir, the slope is positive.
Yes, because slope is positive. Why it is positive means your rate of convergence is, we saw the last question, the rate of convergence is your, oh, is equal to p. So the rate of convergence cannot be negative at all, it is always positive. So p is always greater than 0. So because of this you have a positive slope. This is a negative slope. So 2 is not correct, 1 is correct. And 3 and 4 is not correct because they are not straight lines. So this is the answer. A is A, option A 1. So I hope there are no doubts in this question. We'll go on to the next one. So in the figure shown, which of the following is true? So you have three straight lines. So this is number 1 green color, number 2 red color, number 3 is blue color. So we have 4 options. One has the highest rate of convergence. B option is 1 and 2 have equal rates of convergence. C is 3 has the lowest rate of convergence. Option D is 3 has the highest rate of convergence. So can you guess what could be the answer? So we saw in the last question, right? So you can just apply the same theory and try to guess the answer.
Sir, D 3 is the highest rate of convergence.
Okay. So guess is this one. 3 has the highest rate of convergence. Okay. Just a minute. Okay. Was just checking if the recording is on. So yes, it is on. Not a problem. Yeah. So this was the question we were seeing, right? So yes, answer is D is correct. So we just saw that slope of the graph is nothing but your P, which is nothing but rate of convergence. So if you see among these three lines, this 3 has the highest slope. So highest slope means your value of P is the highest, which is nothing but your rate of convergence is the highest. So D is the correct answer. So in the same question, can anybody guess what is this intercept value? So we saw, right, in the modulus of EM double modulus less than or equal to C times of H power P. So from this taking the log on both sides, we got one expression. So can anybody guess what is the intercept value could be? So we saw that slope is nothing but your value of P, which is rate of convergence. What is the intercept value? Any idea? So if we go back to the last question, we saw that this is mx plus c. So this is your intercept. In this case, your intercept is nothing but log c. Same thing. So this will be log of, so since it is c, you can say it is log c3. Here log of c1 is equal to log of c2. Since both 1 and 2 have the same intercept, so that log c will be same for both. Any doubt in this question?
No, sir.
Okay. So we'll go to the next one. Yes, answer is D. Okay. Stiffness. So FEA solution, underline stiffness when compared to its exact solution. So compared to the exact solution, what does FEA solution predict when with regards to the stiffness? Does it under predict? Does it over predict? Does it exactly predict? or none of the above? Can anybody guess the answer? Any guesses?
Sir, C exactly predicts.
Okay. So one of the guesses exactly predicts. So can anybody say what is stiffness in general? So not the matrix. Means I have yes, of course there is a stiffness matrix as well. But in general, what is stiffness? Can you, in a very simple term, what is stiffness?
Sir, resistance to the force applied.
Yes,
The
resistance to force applied. In other words, it is nothing but the resistance force per unit displacement. Correct? So if you have something like F is equal to K times of U. So if you have U is a displacement, F is the force, then K is the stiffness. So does okay, but does FEA predicted stiffness, is it same as the real stiffness of the system, or is it under predicting or over predicting? So given that your force is going to be some external force, let us say this is not going to change. So let us come to KU. So what about displacement? Does abacus under predict the displacement or over predict the displacement? Any idea? So we have nodal displacements, right? So does it under predict or over predict? Okay, so if you recall from the lecture, there is an expression for the potential, I of u minus I of uh. So this is nothing but, so if your element ranges from 0 to L, if your domain, so some, let us say a by 2 into u dash the whole square dx. So this I is nothing but it represents the strain energy. So this is a potential. So are you able to recall this term?
yes, sir. It's 100 predicts the strain energy.
Yeah. So actually the energy is let us say this thing. So this term is always going to be greater than or equal to 0, since it is a square term and you are integrating. So since this always greater than 0, which means that I of u, sorry, this will be I of uh, I think. Sorry, this is the I of minus I of u. Yeah. So this is strain energy as per FEA, and this is strain energy as per exact solution. So I of is always greater than equal to I of u. So sorry, your energy is over predicted. So can we say that stiffness is also over predicted, since stiffness and energy are related to some extent, right? So more the stiffness, more will be the energy of the system. So if you would have taken this thing, so let us say in this same thing half ku square you can say is the energy. So what is the answer? So energy is all over predicted. So stiffness, is it over predicted or under predicted?
Over predicted, sir.
Yes, over predicted. So answer is B. But what about this displacement? So if you go to the here this expression, so you are considering your external force is going to be the same. If stiffness is over predicted, then u will be under predicted. Okay. So any doubt in question 12?
No, sir.
Okay. So yes, so we have come to the next question. So primary variables converge underline as compared to secondary variables. So there is something called primary variables and there is something called as secondary variables. So primary variables, do they converge at the same rate or slower or faster, or cannot say, none of the above? So can you guess?
Sir, C, faster.
Okay, faster. So basically you will see the answer is C, you are correct. So primary variable is nothing but if you have a problem related to beam or a bar, so your displacement or deflection is a primary variable. Secondary variable is nothing but it is related to the derivatives of primary variable. So we saw that P is equal to K plus 1 minus M. So this is related to the order, right? So for primary variables the order is 0. For derivatives the order could be 1, 2, 3 based on if it is a simple derivative then it's a first order, then if it is a double derivative then it's a second order. So as your M increases your P decreases, which means primary variable have lesser M equal to 0, so they converge faster. For secondary variables they are related to the derivatives. For example you can say EA du by dx. So this is nothing but force in a bar, axial force. Oh sorry. So this force is a secondary variable, whereas u is a primary variable. So secondary variable, which means the derivatives, they converge slower, which means primary variable converge faster. So answer is C. So any doubt?
No, sir.
Okay. So we have I think 2 or 3 more questions. Uh, so after this 2 questions up to question 15 we have a MCQ type of question, then we will try to solve a numerical question. So that numerical will take some long time, so we will keep it in the last. So we will see some for objective question we will see 1 or 2 more. So in a typical Euler-Bernoulli beam problem, which of the following variable is expected to converge the fastest? So you have deflection, you have slope, you have bending moment, you have shear force, you have strain energy. So which of the variables is expected to converge the fastest in a typical Euler-Bernoulli beam? So can you take a wild guess? Fastest. So we just saw in the last, fastest means it occurs usually for the primary variables. So which of the following could be a primary variable? There is a deflection, there is a slope, there is a bending moment, there is a shear force, there is a strain energy.
Sir, A, deflection.
Okay, deflection. So you see the answer. Yes, you are right. So there are different terms, right? So if you say, what you ask, what is the governing differential equation, it would be something of this form. So d square by dx square of e I times d square u by dx square is equal to some q of x. So what is u in this? U is nothing but your deflection, correct? Okay. So what is du by dx? So let us say this is your beam, this is x, so it deflects something like this. Sorry. So u is a downward, in this case it's a downward deflection, it could be upward also. So what is du by dx?
Rate of change of direction.
Yes, rate of change of deflection. What is, so in these 5 options, what could be the thing that matches with the rate of change of deflection with respect to x? Instantaneous. It's nothing but the slope, right?
Slope, yes, sir.
So have any curve yx, so you have something like this. At that particular instant, your dy by dx is nothing but your slope. Same here. So u is a vertical displacement or deflection in this case. So du by dx is nothing but the slope. So you can see, compared to deflection and slope, which will converge faster. So u is a 0, order is 0 because there is no differentiable term at all. Du by dx is a first order derivative. So deflection will converge faster. So this is one example. Okay, we'll see the next question now. So we saw the answer is A. So same question, which of the following is expected to converge the slowest? So this is you need to think. So what are the orders of differentiability for each term? So if you guess this correctly, then you can get the answer. So which of the following variable is expected to converge the slowest? Can you take a wild guess? Just think about it. Maybe I'll give you some 1 or 2 minutes. So try to recall the differential equation. What are the possible terms? So u we saw is the deflection. Then du by dx we saw is the slope. So what could be the expression for bending moment? What could be the expression for strain energy? What could be the expression for shear force? So any guess? Can take your time. So again I'll recall the differential equation. D square by dx square of E I d square u by d x square is equal to some q of x. So this is your equation, differential equation. This is the governing differential equation for the bending of a beam. So recalling the last equation, last question, we saw u is the, if u is the deflection, du by dx was the slope. So you have to guess what could be the expression for the bending moment, shear force, strain energy, deflection and slope we already have. So after guessing the possible terms, so you can try to answer. There is lot
Sir,
of yeah,
D is shear force.
shear force. Okay. So yes, shear force is your guess. Okay. We'll see the answer first. Yes, you are correct. Shear force is the answer. So what could be the bending moment expression? Can anybody guess? We have du by dx. Bending moment, then shear force. So this ei du by dx square is nothing but your bending moment only. So if you recall, there is a classic equation for beam bending. M by I is equal to sigma by y. So your m is nothing but I sigma by y. So you have your I. The sigma is nothing but your E times of strain, Young's modulus. So if you calculate, if you work it out, you will get something in the form of E I into d square u by dx square. So shear force is nothing but rate of change of bending moment. So this will be minus d by dx of E I d square u by dx square. So this is a second order. This will be differential of second order, which is a third order. Sorry. So strain energy, if you see, that is also will be a second order. So why it is a second order? You have something like some half into EI into d square u by dx square the whole square. Something like this. You have the energy, strain energy. So here also the order is 2, shear force is order is 3, bending moment order is 2, slope is order is 1, deflection is order 0. So slowest convergence means your order of differentiability should be higher. So shear force has the highest differentiability. So answer is D. So any doubt? Why D? Why D is the answer? Yes, you have guessed it right. So this is the explanation behind this. Why D is the answer. Any doubt in this?
No, sir.
Okay. So we saw some 15 questions actually. So this was the objective type of question. So so we have one more question which is a subjective type of question. So we will try to work this question. So consider the following differential equation. You have your differential equation. So minus d square u by dx square is equal to 2. This is your domain 0 to x to 1 with boundary conditions. U at 0 is 0, same u at 1 is also equal to 0. So find the energy norm and L2 norm error for the following cases assuming linear elements. Number of elements you can assume in one case it is n is equal to 2 and n is equal to 3. So this is the last question. This is a numerical question. This numerical question we are going to step by step going to try to solve it. So for this, so first of all, can you recall what is the energy term, energy norm? And what is L2 norm? So I'll just recall the expressions here. Energy norm is Em. So this is equal to, so integral A to B. So summation I is equal to 0 to m d power I of u by d x power I minus d power I uh by d of x power I think the whole square will come, I think. Yes, you have a whole square into dx. So this integral, this entire thing I am going to take a square root. So this is the energy norm. So L2 norm is nothing but if you put m is equal to 0, you are going to get the L2 norm, which is nothing but integral of A to B u minus uh square dx the whole power half. So these are the energy norm. This is the L2 norm. For finding energy norm L2 norm, first we need to solve for what is uh and u, and then we have to substitute in this and we are going to get the expression. So instead of this thing, I am going to go for this note so that it will be easier for me to solve. So I am going to go for this. So are you able to see the note?
Yes, sir.
Okay. So we'll again first we'll try to solve the exact solution. So minus d square u by dx square is equal to 2 for 0 x less than 1. So this was, and we had u of 0 is equal to 0, u of 1 also is equal to 0. So the what I am writing are you able to see right in the note?
Yes, sir. Yes.
Yeah, okay. So next is, for exact solution I am just going to integrate it twice. So integral 0 to 1 minus d by dx of du by dx is equal to into dx is equal to 2 times of dx, right? So which means du by dx sorry, I will just do the normal integral. I will not have the limits. I later I will do the limit. So this just I am going to integrate. So if I just integrate, this will be 2x plus some constant c1. Again, if I am going to do du is equal to 2x plus c1 times of dx. If I integrate this, I will get u is equal to 2 into x square by 2 plus c1 times x plus c2. So this integration is fine, right? X square plus c1x plus c2. This is u. This I have just integrated twice. So I am just finding the exact solution. After finding exact solution, we are going to find the FEA solution. And after finding the FEA solution, we are going to substitute both in the energy norm and the L2 norm. So that is the procedure. So if I put, I have two cases. U of 0 is equal to 0. So if I substitute it, 0 square plus c1 into 0 plus c2 is equal to 0. So this gives me c2 is equal to 0. So now my u becomes x square plus c1x. So c2 is 0. Now again if I put u of 1, same again the next boundary condition, u is equal to x square, sorry, so while I am also you can also simultaneously try to solve it. So 0 into, sorry, 1, again sorry for this, 1 square plus c1 into 1 is equal to 0. So c1 is equal to minus 1. So therefore u is equal to x square minus x, which is equal to x into x minus 1. So this is my exact solution. So any doubt in this exact solution? We just
No, sir.
integrated and we then use the boundary condition. So now FEA solution. So your differential equation is minus d square u by dx square is equal to 2. So I am first going to assume just two elements. So let us say each element has length h. So 0 to 1. So this will be 0.5. So which means h is equal to 0.5. So this is this thing. So this is element number 1, this element number 2. Step 1, discretization of domain. We have done the discretization, which means that we have divided the domain into two elements, each with a length of 0.5. So here h is 0.5. So if I take one particular element and local coordinates, so 0 to h, this will be the local coordinates. Same way for this element also, the local coordinate will be 0 to h, but global coordinate will be 0 h to h. This will be local, this will be global. So step 2 is for assumption of interpolation function. So we are going to use linear interpolation. So what is linear interpolation? So for u for the element, so u is equal to, I am going to put summation I is equal to 1 to n u I into psi I. So psi is the, sorry, let us say this is j, uj psi j the weight function, sorry, not weight function, psi j is the interpolation function. So in our case n is equal to 2, so which means u is equal to summation j is equal to 1 to 2 u uj psi j e, which is nothing but u1 psi 1 plus u2 psi 2. So how the interpolation function we are going to assume? Where it has gone. Okay. So psi 1 is equal to 1 minus x by h, psi 2 is equal to x by h. So the nature of interpolation function, we know that this is 0, this is h. So psi 1 ranges like this. So at x it is 1, at x equals 0 it is 1, at x equal to h it is 0. So it goes like this. This is psi 1. Then psi 2 is exactly the opposite. Here it is 1, here it is 0. So this is a linear interpolation. So this is done. As the assumption of interpolation function is done. Step 3, weighted residual integral. So minus d square u by dx square is equal to 2. How I am going to do the weighted residual integral is integral from 0 to h. This is for an individual element 0 to h, minus d square u by dx square minus 2 into w dx is equal to 0. This w is a weight function. So in our case the weight function is going to be the same as psi I. It is nothing but same as interpolation function. So here I also ranges from 1 to 2. So you have psi 1 and psi 2. So you have two weighting functions, psi 1 and psi 2. This is weighted residual integral. Now step 4, weak form. Okay, so integral 0 to h minus d by dx of du by dx minus 2 into w dx 0. So I am writing this d square by dx as d by dx of du by dx. So now I am going to split the integral 0 to h minus d by dx of du by dx into w into dx minus integral 0 to h 2 times of w dx is equal to 0. So how I am going to do the weak form? I am going to use this formula, integral of w dv is equal to wv minus integral of v dw, integration by parts. So this is nothing but weak form. I am trying to transfer my differentiability from this what you can call primary variable to the weight function. So v in this case is nothing but du by dx. So transferring differentiability from primary variable to weight function. So if I take this circle, if I take this will become integral 0 to h du by dx into dw by dx into dx minus w du by dx from 0 to h minus integral 0 to h 2 w dx is equal to 0. So till here, is there any doubt? We are doing the element at element level. We are forming the weak function and trying to get the element level equation. Any doubt till here? Are you able to follow?
No, sir.
Okay.
Yes, sir.
Yeah, fine. So now we have to, for u and w, we just saw u is equal to summation j is equal to 1 to 2 uj psi j, and w is nothing but psi I. So if we try to substitute in this, so this I will take to the right hand side, this both. So integral 0 to h d by dx of summation j is equal to 1 to 2 uj psi j into d psi I by dx into dx is equal to, so this you can term as psi I into d by dx of summation j is equal to 1 to 2 uj into psi j. This is boundary term 0 to h plus 2 integral 0 to h psi I dx. Okay. So if I try to take this summation outside, so this uj, these are now going to be by nodal values. So these are constant, these are what unknown constants. The psi j are known function. Same thing for psi I also. Psi I and psi j are just same, only the subscript varies. So if I take like this, summation j is equal to 1 to 2 d psi I by dx into d psi j. So this also e I am just putting for it means the superscript means particular element. So d psi j e by dx into uj dx integral 0 to h is equal to some psi I into, let us expand this term, d by dx of uj, the j is equal to 1 to 2 means u1 psi 1 plus u2 psi 2. So this differential and the whole term at I am evaluating at the 2 points 0, 0 and h, which are the end points of the boundary points of the particular element, and this is plus 2 into integral of 0 to h psi I dx. So totally how many equations I am going to have? I am going to have actually 2 equations totally, but you will have 4 terms corresponding to I equal to 1 comma 2 and j is equal to 1 comma 2. So this is nothing but you can say this is your kij into uj is equal to some f fi you can say. So this is this thing. We will try to further evaluate. So what is kij? Is equal to integral 0 to h d psi I by dx into d psi j dx into dx. So this uj I am taking outside here, kij into uj. So whatever is remaining is my kij. So we will now try to evaluate what is each value. So k11 integral 0 to h d psi 1, sorry, this is not I, this is going to be 1. Psi 1. Can you recall what is psi 1? We long back we defined what is psi. So psi 1 is 1 minus x by h, psi 2 is x by h. X is the local coordinate. So what is d psi 1 by dx? It will be minus 1 by h. Is it correct?
Yes, sir.
Okay. So I hope this is a little long question. So I hope you are able to follow line by line. I am trying to solve in this manner. So this is 1 minus 1 by h. Same thing. This is also minus 1 by h into dx. So 1 by h square I take outside. 1 by h square into 0 to x dx is h. So 1 by h. k12 integral 0 to h d psi 1 dx d psi 2 by dx into dx. What is psi 2? X by h. So d psi 2 by dx is equal to 1 by h. So I am going to substitute minus 1 by h into 1 by h dx. So this is minus 1 by h square integral 0 to h dx. So this is minus 1 by h. And k21 will be same as k12. So this is nothing but integral 0 to h d psi 2 by dx to d psi 1 dx into dx. So 1 2 I am just replacing by 2 and 1. This was 1 by h, this was minus 1 by h dx. So same thing, minus 1 by h you will get. K22,
1 by h.
yeah, 1 by h. So again, if I were to do line by line, you will be have psi 2 at both ends. So this is also 1 by h, 1 by h. So 1 by h square dx 1 by h. So you have my K matrix. For this particular element is 1 by h into 1 minus 1 minus 1 1. This is correct, right? So I have my LHS k into u. So this will be, so u is nothing but u1 and u2, and this is only for the particular element. I have two elements. For each element this is valid. The length is h. This is u1 and u2. This is for locally. So k and u are ready. So what I have to evaluate is, I have to evaluate RHS. Let us see what is RHS. So RHS, I am going to split into two. So this was the equation, right? So my RHS, let me say I take this color. So this is the boundary term, because I am going to evaluate it only at the 0 and h boundary, and this is another RHS term. So let me call this 1, let me call this 2. So here, so you call kij into uj, summation j is equal to 1 to 2, and I also equal to 1 to 2. So which means k11, k12, k21, k22 into u. So all these are with respect to element. So here I is equal to 1, I is equal to 2, here j is equal to 1, j is equal to 2. So how I am going to evaluate RHS is, first I take this boundary term, it was psi I into u1e, sorry, I will go back again, psi 1 into d by dx of u1 psi 1e plus u2 psi 2e. The whole thing I am going to evaluate at 2 points 0 and h. So I have psi I, so which means I is equal to 1 and 2. So corresponding to I equal to 1, I will have one term here, and corresponding to I equal to, I will have another term here. So for I equal to 1, so psi 1 into this d by dx I am going to expand. So which means it is u1 d psi 1 e by dx plus u2 d psi 2 e by dx at the whole thing from 0 to h. So one thing I can be sure, psi 1 is equal to 1 minus x by h. At x equal to h, which is this thing, my psi 1 is equal to 0. So this whole thing cancels out for h is equal to, for this h upper term. So which means I am going to be having this term. So I am going to have minus term. So this whole thing, if I say is b, so b at h 0 is equal to b of h minus b of 0, correct? So this whole thing is vanishing, because at h your psi 1 is 0. So whatever this inside term, it will multiply by 0, it will give you 0, and psi 1 at x equal to 0 is 1. So if I going to evaluate this minus this whole thing, this psi 1 is going to be 1 u1 d psi 1 e by dx plus u2 d psi 2 e by dx. This is whole thing is minus, so which means what is d psi 1 by dx minus of minus 1 by h, correct, plus u2 1 by h. Is it okay? D psi
Yes.
d psi 1 and d psi 2 we saw previously, right? So if
Yes.
I expand it, so u1 times e into 1 by h minus u2 into 1 by h. Okay. So boundary term we have evaluated for I is equal to 1, right? And this is for 0, correct? This whole thing I am evaluating at 0 because yes, this whole thing I am evaluating at 0. So now for I is equal to 2, I just go up, I just recall. So this psi I, it was the this thing. So psi I, so I is equal to 2. This all thing remains the same. This psi becomes psi 2. Psi 2 into d by dx of u1 psi 1 plus u2 psi 2. So the whole thing again evaluated on 0 to h. So psi 2 we see is equal to x by h. So this entire term psi 2 vanishes at x equal to 0, it vanishes. Okay, which means so this entire thing is going to be only psi 2 e into this, again I am going to expand, sorry, only at h. At 0 the entire term vanishes because psi 2 becomes 0 at x equal to 0. So which means this psi 2 at x equal to h is 1. Why? Because psi 2 was x by h. So h by h 1. So now I am going to evaluate u1e. Okay, I am going to directly substitute the value. What is d psi 1 is minus 1 by h plus u2e 1 by h. at this entire thing at h. Any doubt till here? So here this is for I equal to 1, this is for I equal to only the boundary terms. Any doubt till here?
No, sir.
Okay. So we have the boundary term. Next is we have the this second term 2 times integral psi I dx. So for I equal to 1, 2 integral 0 to h psi 1 dx. So 1 minus x by h into dx 0 to h. So this is h minus 1 by h into h square by 2. This is h by 2. And at I equal to 2, okay, it was 2 times I think. Oh, okay, the entire thing into 2. H 2 times integral psi 2 dx 0 to h. Psi 2 is 2 x by h dx 0 to h. So 2 by h into integral x dx from 0 to h, 2 by h into h square by 2, again h. So which means, so RHS we are divided into 1 plus 2 boundary term, let us say this is non-boundary term. So this is h, this is h, correct? And what was 1? This whole thing. This whole thing and this thing, correct? This whole thing evaluated at h. Or I'll try to simplify this rather than keeping it like this. So let us say it is some b1 b2. So b1 so this h I can take 2 inside. So u1e at h into minus 1 by h okay for this sorry I have to at 0 u1e into 1 by h at 0 into 1 by h plus u2e 0, this is minus 1 by h. This is what we saw, right? So this plus I am putting here and 1 by h I am taking inside. So this is this thing b1. Then b2 is equal to say similar thing. Yes, this one. u1 at e of h into minus 1 by h plus u2e at h into 1 by h. Was this the relation? Yes. So this h subscript which means that so this is my b1 and b2. So for element 1 my equation is k11 k12 k21 k22 at e into u1e u2e is equal to some b1 plus b2. This is also related to the element plus this term we evaluated, second term h. Okay. So similarly for element 2 also we can write. I'll just instead of e I'll just put it as 1. 1 1 1 1 1 1 1 1 and this HH is common. Element 2 same thing k11 k12 k21 k22 2 2 2 2 b1 b2 at 2 plus h. Okay, so now this is element wise we have get the equation. Till here any doubt?
No, sir.
Element wise we have got the equation. So next step is it step 4 or step 5? This step 4 weak form we got the element level equation through weak form. So step 5 assembly. So how to assemble? So we have this element, this is element 1, this is element 2, this is node 1 2 local, and for this is 1 and 2. At global this is 1 2 3. So u2 is equal to, sorry, u2 of 1 u2 of the first element and u1 of the second element, both are equal to u2. So this will be my u1, this both will be u2, and this one will be u3. Is it correct? While
Yes, sir.
assembling, right? So my
Yes.
yes. So while assembling this thing, so you will have k11, k12, k21, k221 plus k112, k12, k21, k22. So this will be 0. So this will be your u1, u2, u3. So this will be your LHS. Okay. So this will be B11, this will be B B21 plus B12, and this will be B22. Correct?
Yes, sir.
And this will be H 2H H.
2H.
Because why 2H in the middle is,
So we added H
yes,
plus
this H and this H are going to get added. Okay. So in net effect, now we have to see what are the things now. So what is K11? I think it was 1 by H, right? So 1 by H into 1 minus 1 minus 1. This will become 1 plus 1 2.
2.
This will also be minus 1 minus 1 1 into u1 u2 u3. So this thing will be little confusing, so we'll have to see term by term. We have got to see that. So what is B11? So this is B1 and B2. Okay. So I'm going to write B1 and B2. We'll settle this stuff. Here I'm going to write again B1 and B2. Because boundary term will be very confusing. So u1 plus u2 at 0. So I'll again put subscript 1, u11 at 0, u11 at 0 into 1 by h. See? Yeah, 1 by h plus u2 at 0, u2 1. 1 by h plus u2 1. This is also at 0. Is it at 0? Mm. 2 minus 1 by h. So this is B11. So B21. u11 1 u11 at h minus 1 by h plus u21 at h into 1 by h. So what is u11? It's nothing but u1. u21 is in u2. Correct? This is local, this is global. Similarly, I am going to write b1 and b2 for second element. b12 this is going to be h. Again here u12 u2 u22 is u3 1 2 1 2 global 1 2 3. So in this we will try to eliminate some terms. Okay, so for a particular element, so at this node it is u1, so at this it is u2, and here 0 0 h. So this can be element 1 or it can be element 2 also. So u2 1 of 0, does it make any sense? So first element u2 at location 0, what is it? u2 at location 0 is 0, right?
0, yes.
Because u2 is defined only at location of h, so this I can straight away cancel. Similarly in this one, so u11, this also I can get a 0, right? Because u12 u2 is defined only at h and u1 is defined only at 0, so u1 of h is 0 0. So similarly for here I can cancel this as 0, and for this I can cancel as 0. Is there any doubt?
No, sir.
Okay, so only some more time, I will quickly finish this now. So my b11, so I am going to make everything in global terms now, u1 into 1 by h. So b21 is equal to u2 into 1 by h. b12, so u12 again, this is u2 into 1 by h. B2 2 U3 into 1 by H. Okay. B. Okay. Okay. So finally, I'm going to write this equation. One by H times minus 1 2 sorry this is the equation. So now we have to apply the boundary conditions. Okay. So u1 and u3 are 0. Since my boundary condition states that u of 0 and u of 1, both the extreme points are 0. So which means this is 0, this is 0. Again u1 u3, this will also be 0. So we are going to have only one equation in the middle. So 2 by H. So just we'll have this middle terms. U by H into U2 plus is equal to okay. So somewhere there is a mistake. H2H 0. Okay. Okay, I think this entire thing should have been minus. check once more. Mm, okay, in the boundary term I think there is some error. Let me look at it once again. Because the boundary term at 1 and 2 they have to vanish actually. H. Zero. Okay, we'll see this. So this actually should be 0. It should come minus. Somewhere I have made mistake. So let us see. So this will be 2h. So u2 is equal to h square. This is what I am getting. So u1 is 0, u3 is 0. So for element 1, this is 0 to h. U is equal to 1 minus x by h into 0 plus x by h into h square. For h to 2h, u is equal to h square so this can you guess how this term occurs? We assume that u is equal to uj psi j, correct, for at element level. So from there we get this term. So sorry, x by h to hx. So here 1 minus x by h to h square. Here h by h to h square. So this is the u value. So this is your UH. UH will be from 0 to H one value, and from H to 2H another value. So now what we had initially planned to do is calculate the energy norm and L2 norm. L2 norm is very simple, U minus UH the whole square dx integral 0 to, you have to do 2H over here because entire domain, square root, and energy norm summation I is equal to 0 to 1 d power I u by dx power I minus d power I by UH by dx power I the whole square dx is integral 0 to 2H for half. So this you can, since it is already time, so you can try to calculate this term, and you can try to calculate what is energy norm and what is L2 norm for each. So this is how we are calculating. So I will again check my calculation in the boundary term case. I will see where I have made the mistake. So meanwhile, I think with this we can close the today's session. So any doubts other than this last question? So in the MCQ, was there any doubt? MCQ questions?
No, sir.
Okay.
No
So
doubts.
okay. So this alone I will check once again. I will maybe get back to you in the next session. So with this, can we close the session?
Yes, 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 sir.
Okay. So thank you for attending. So we'll look for the forward to the next session, same Monday 6 to 8, and with that we'll go for the week 3 contents next week. Okay. Shall I close the meeting now?
Yes, sir. Thank you, sir.
Okay. Thank you.